Hello there. My name is Rafael Nogueira Cunha. I'm a web developer and student in the Federal University of Rio Grande do Norte in Brazil. This article was written in partnership with the University of Brescia for the 2020 IEEE International Workshop on Metrology for Industry 4.0 and IoT. Our article is about introducing a survey methodology for assessing LoRaWAN coverage in smart campus scenarios. We are going to talk about an introductory part on the concept of IoT, LoRa, and smart campus, the known methodologies and the one that we have used, our coverage results, and the conclusions about the efficiency of the proposed methodology. In a very simplified way, Internet of Things spreads sensors across environments, quickly bringing measurements to the Internet, where these can be processed to make decisions. With a network of connected devices, valuable data is gathered and shared. Data that let us better understand how these things work and work together. This remote monitoring activity has become essential in modern society. Water and electric power consumption, traffic and public transportation schedules, industrial productive chain, and many others are some of the examples of monitoring activities that can be easily checked through any device connected to the internet. One of the protagonists in this new reality are the connectivity technologies. They differ in many characteristics such as transmission speed, range, cost of infrastructure, transmission cost, battery consumption, etc. With regard to reach and power, there is a category of transmission technology that aims to send data over long distance with low power consumption, called Low Power Wide Area Network, the LP1. LoRa is a spectrum modulation derived from chirp spread spectrum. It enables long-range communication link. Through LoRaWAN protocol, it's possible to manage the communication between LP1 gateways and end-node devices. LoRaWAN provides an affordable network infrastructure that allows many independent applications, making possible and viable the digital transformation of a campus on a smart campus. LoRaWAN works with a star topology, where devices send packets straight to LoRa gateways. These, connected to the internet, forward the received packets to a LoRaWAN backend, who will process and deliver the information to the final application. The digital transformation of a campus into a smart campus is possible due to the affordable network infrastructure LoRaWAN provides. In the process of integrating the concept of IoT within the campus infrastructure, a good deployment of the LoRaWAN gateways will reflect on important factors: the costs of the network infrastructure, the transmission quality, and the user experience with the whole system. The placement of the gateways becomes a key factor for the success of this digital transformation process. The coverage of wireless technology can be estimated using mathematical model related to propagation of electromagnetic waves. Unfortunately, the complexity of real scenario, especially when urban landscape are considered, quickly reduces the accuracy of such approach. In the literature, there are previous works, including some paper of the authors, that describe valid methods to execute survey in a smart campus scenario. The main drawbacks of such approaches are the long duration of the experimental phase and the difficulties to trace changes of coverage range over time. For this reason, this paper proposed a new approach based on cloud-centric systems for the automatic creation of coverage range maps in complex scenarios. The proposed approach is aimed to create a survey system that works in automatic. LoRaWAN transmission and reception data is collected and processed in the cloud. In order to do so, Many transmitting nodes are possible, each one connected to the internet and sending its information to a common IoT platform. On the other side, at the LoRaWAN backend, network information are also sent to the same IoT platform in order to be merged. Values like position of transmission, type of transmission, transmitting power, receiving signal strength indicator, and signal to noise ratio are collected in a centralized way, processed, and then shown in a meaningful way to the end user. At last, a detailed survey report is produced in automatic. The proposed methodology has been applied to a real use case, the Smart Campus of the UFRN in Natal, Brazil. The platform and the software needed for the survey have been mapped to existing hardware and software stack, with the aim of reusing as much as possible the available infrastructure on the campus. In particular, the following infrastructure and device has been developed or customized. SIO has been used as the cloud platform for data collection. This platform allows gathering data from sensors in the cloud for processing and for intuitive visualization, in addition to allowing control of devices by sending commands to actuators located remotely through a web interface. This picture illustrates the SIO interface with the latest sended data from the LoRa device. Chirp Stack has been used as LoRaWAN software stack. The LoRaWAN service stack is connected to the gateway and it's responsible for storing and processing LoRaWAN packets redirected from the gateway. Laird Centrus RG186 is the LoRaWAN gateway, working on a frequency interval of 863 to 870 MHz. The microchip RN2483 has been used for the LoRaWAN modes. Connected to a notebook, it was configured for a wide range transmission, prioritizing transmission range over speed. In addition, as the LoRaWAN mode does not have GPS, a portable GPS receiver interfaced with the PC was used to get the coordinates of each packet sent. A car was used for the transmission tests to move around several places in the campus while the mode sent data to the LoRa server. The information from the real-time measurement panel helped in the execution of the tests. When the current distance prevented the delivery of packages, we looked for areas closer to the gateways in order to obtain more information in the areas with coverage. The data storage in this process works as it follows. The device sends its data via LoRa to the gateway, and this data is written in base64 format. And after received, this data is redirected by the LoRa gateway via HTTP to SIOT's backend. SIOTs then translates this encoded data into valuable information and send it to a non-relational database for storage and for future usage or monitoring. After the transmission tests, all stored data was processed into a table with altitude, distance, average and standard deviation of received signal strength indicator, and average and standard deviation of signal to noise ratio of each visited point. In parallel, a map was defined using the portable GPS receiver coordinates of each visited point. The table and the map can be seen in the next slide. The distance and altitude described in this table are all relative to the gateway position. In the map, some of the visited spots are shown, and the green and the red balloons shown the delivered and not delivered packages, respectively. The blue circle at the bottom of the map shows the gateway position. The polygon formed by the green balloons and highlighted with a semi-transparent area shows the coverage area according to our methodology, which in this case is approximately of 36 hectares with a maximum range of 753 meters from the gateway. The major conclusion regarding this location is that this can be possible due to its elevation. It stays more or less at the same altitude of the gateway as observed in the table. It can be observed in the map that from the further location at 911 meters, it is not possible to send successful packets. On the contrary, some packets that were sent from places much closer to the gateway were not successful because of the campus is an urban area and contain many physical obstacles that may cause loss of signal. Such results show that the coverage in a real environment is easily evaluated with propagation models. It can be seen that the greatest distance achieved is much less than expected because of network topology, terrain morphology, and other deployment limitations. Moreover, even considering the 750 meters reached, this distance is not repeated in other directions because of the obstacles. In conclusion, the results confirm the need of an accurate and experimental survey of the coverage area for planning the communication infrastructure of any real distributed acquisition system based on LoRaWAN. The proposed methodology for automatic creation of coverage survey of LoRaWAN is really useful in practical scenario where the complexity of the terrain and the number of variables cannot fit traditional propagation models. Based on cloud-based centralized collection of data, derived both from transmitting node and receiving gateways, the proposed methodology is able to produce meaningful results, reducing the effort of people involved in the survey. The considered use case showed that an accurate survey is important because the covered area can be very irregular in a real environment. There may be many impairments in a real environment between the moat and the gateways, hindering the success of the communication.